Hi everyone, I'm Cheryl. In this problem, we're asked to use Lagrange multipliers to help us maximize my production function. My production function is 100 x to the 0.25, y to the 0.75. That's the Cobb-Douglas model for production. Now, in order to use Lagrange multipliers, we need to not only have the function that we're going to maximize, but also a constraint. We're going to get the equation for the constraint based on the fact that we know that the cost of labor is $112 per unit, the cost of my capital is $60 per unit, and the most I have to spend on my labor and capital is $250,000. So let's go ahead and write a constraint. Because I want my production level to be maximum, I want to use the entire $250,000. So let's let X represent the number of units of labor. So that means that I can spend 112 times X dollars on labor. Let's let Y be the number of units of capital. So that means I'm going to spend 60 times Y dollars on capital. And that total is going to be $250,000. Okay, so let's begin our Lagrange multiplier process. So what I want to do is I want to take the gradient of P of xy and set that equal to my Lagrange multiplier lambda times the gradient of my function g of xy. Well, what is that function g of xy? Remember, it comes from my constraint. So I'm going to write the function g of xy as 112x plus 60y minus 250,000. All right, so when I look at my equation, the first thing I need is the gradient of P. So I want to take, first of all, the partial with respect to X. So I'm going to treat Y as if it's a constant. So that means that the 100 and the Y to the 0.75 is a constant multiple. And then I'll differentiate X to the 0.25 power. So that's going to be 0.25 times X to the minus 0.75 power. And that will be multiplied by my vector I. Next, I want to take the partial with respect to Y. So I'm going to treat the 100 and the X as a constant. So 100 X to the 0.25 will be a constant. And I need to differentiate Y to the 0.75 power, which is going to be 0.75 times Y to the minus 0.25. And that will be multiplied by my vector J. Okay, so that's my gradient of P. This is going to be equal to my Lagrange multiplier lambda times the gradient of G. So the gradient of G is going to be 112i plus 60j. So now let's simplify this equation. I've got 100 times 0.25, so that's going to be 25 y to the 0.75 and x to the minus 0.75 times my vector I plus, I've got 100 times 0.75, so that's going to be 75 x to the 0.25 y to the minus 0.25 times my vector j, and that's going to equal 112 lambda I plus 60 lambda times my vector j. Okay, so in the process of Lagrange multipliers, what I want to do is make sure that the I component on the left-hand side of this equation is equal to the I component on the right-hand side. So that means that I have 25 y to the 0.75, x to the negative 0.75, being equal to 112 lambda. When I equate the j components, I'm going to have 75 x to the 0.25, y to the minus 0.25 being equal to 60 lambda. So 75 x to the 0.25, y to the minus 0.25 is equal to 60 lambda. All right. I have one more equation that I need when I use my Lagrange multiplier technique, and that is my constraint equation. So I also know that 112x plus 60y minus 250,000 is going to equal 0. And I now have a system of 3 equations with 3 unknowns. So I need to solve this system. Okay. So I'll begin by combining those first 2 equations. So I know that I can solve each of those equations for lambda. So when I do that, my first equation is going to become 25y to the 0.75 x to the minus 0.75 all over 112 equals lambda. And for my second equation, I'll have 75 x to the 0.25 y to the minus 0.25 all over 60 also being equal to lambda. Okay, so because both of these equations are equal to lambda, I can set those 2 left-hand sides equal to each other. So what do I have? Well, I have 25y to the 0.75 x to the minus 0.75 all over 112 being equal to 75 x to the 0.25 y to the minus 0.25 all over 60. Okay, now what I'm going to do is I'm going to take this equation and try to express y in terms of x. I'm going to need to do some number crunching for that, so I'm going to pull out my calculator because I don't think I can do this in my head. Okay, so we're going to begin by multiplying both sides of my equation by 60 and then multiplying both sides of the equation by 112. So when I do that, I'll begin by taking 25 times 60, and that's 1,500. So I have 1,500 y to the 0.75 x to the minus 0.75, and then I'll multiply 75 times 112 and get 8,400 x to the 0.25 y to the minus 0.25. Now I'm going to rewrite both sides of my equation, getting rid of my negative exponents. So the way I'm going to do that is I'll write this as 1,500 y to the 0.75 divided by x to the 0.75. And on the right-hand side, I have 8,400x to the 0.25 all over y to the 0.25 power. Multiplying both sides by x to the 0.75 and y to the 0.25 power, I notice that I'm going to end up with 1,500 times y to the first power, and that's going to equal 8,400 times x to the first power. So I'm going to go ahead and solve this for y. Y is 8,400 all over 1,500 times x. And I notice that I can divide both the top and bottom by 100, so that cancels. And also I notice that 3 will divide evenly into both 84 and 15. So 84 divided by 3 is 28. So y is going to be 28 over, and 3 goes into 15 5 times. So 28 over 5 times x. So now I have a relationship between x and y. The next thing I'm going to do is I'm going to take this expression and plug it into that third equation. So what we have then is 112 times x plus 60 times y. And instead of y, I'm going to write it as 28/5 times x minus 250,000 equals 0. Okay, so again, I noticed that 5 divides into 60 12 times. So I have 112x plus 28 times 12. So 28 times 12 is 336. So that's 336x. I'm going to go ahead and move that 250,000 to the other side. So it equals 250,000. So 336 plus 112 is 448. So I've got 448x equals 250,000. And dividing 250,000 by 448, I come up with x being equal to approximately 558. Now, it's actually a little bit bigger than 558, but remember, I want to make sure that I don't exceed my $250,000 target for the total amount spent. So I'm going to make sure I've rounded this down just a little bit. So it looks like I'm going to get my maximum production when I use 558 units of labor, because remember, x represented the number of units of labor. Next, I have to figure out how many units of capital I need. Well, I can do that by plugging my x value into that third equation to calculate y. So that tells me that I have 112 times x, which I now know is 558. I'm going to add 60y, subtract 250,000, and that should equal 0. So 112 times 558 is 62,496 plus 60y minus 250,000 equals 0. So I'm going to add 250,000 to both sides and subtract 62,496 from both sides. And when I do that, I end up with 187,504. And finally, I'll divide both sides by 60 to get approximately, and again, I'm going to use an approximately here, 3,125 units of capital. And again, I've rounded this one down to guarantee that I keep within that $250,000 budget that I have. Okay, now, using Lagrange multipliers, this tells me that I have an extrema when x is 558 and y is 3,125. Based on my production model and also the constraints that I have, I know that's going to be a maximum. So the only thing left to do is to actually tell you what that maximum production level is. So what we're going to do is plug these two numbers into my production formula. So I know that I will have a maximum production when x is 558 and when y is 3,125. So this is going to equal, according to my model, 100 times 558 raised to the 0.25 times 3,125 raised to the 0.75. So if I do some number crunching here, 558 raised to the 0.25 power times 3,125 raised to the 0.75 power, and then take that answer and multiply by 100, I find that my production level is approximately 203,140. And again, this is an approximation. I've rounded my answer. I hope that was helpful. Thanks.